Yeah, I just wanted very briefly to introduce Connor. That Connor, but as you see that, but here he has 10 published papers, that 3 journals, 7 conferences, and 9 papers. He is the first author. Also, he won the best paper award at IEEE conference on tools with AI, and based by the paper award there. And also, he has more about 7,000 citation to his papers. With that, Connor, please start your defense.
Thank you so much, and thank you everyone for attending my dissertation on data augmentation and deep learning. Before getting into any of the technical details, I want to thank everyone who was involved in my education at Florida Atlantic University, my advisor and mentor, Dr. Taghi Koshgofter, who I've been meeting bi-weekly for nearly 5 years over developing my education in machine learning science. And I'm also super grateful to everyone in the supervisory committee who I've taken many courses with. Dr. Nojuman, who taught me data structures, Dr. Dingding Wang, who taught me natural language processing, Dr. Xingquan Zhu, who taught me the math behind neural networks and deep learning gradient descent, and Dr. Ferd, who taught me operating systems and multimedia data systems. So thankful to everyone who was involved in my education at Florida Atlantic University. So as Dr. Koshgofter mentioned, published about 10 papers. So I guess I'll just gloss over this quickly, but so to give a quick introduction to the presentation before diving into it, there's going to be kind of 3 sections where I'll start with kind of a theoretical tour of concepts in deep learning. Then we'll dive into the experiments that I conducted during my dissertation research. And with the covering of the experiments, I've kind of opted for giving you the high-level overview. If you want to know like the real technical details of the experiments, you can consult the dissertation, the writing. And then we'll conclude with like kind of like some future directions and things like this. Great. So we'll start off with an introduction to concepts in deep learning. So to start off, kind of the core of deep learning is about data. Deep learning is a data-driven technology. And so maybe to all get on the same page in a very basic sense, data describes measurements about the world. And data takes all sorts of different forms. You can have tabular data, images, text, time series, biological sequences, graphs. And one of the most interesting things is really understanding the nuance of these shapes of the data, whether they can be fit into vectors, matrices, tensors, kind of the distributions of each of the values and things like this. So if you see my mouse, the tabular data, you have a mix of features like numeric features, categorical features, binary features, and you combine them into these feature vectors. Image data, like this photograph of a famous church in Milan, is this high dimensional pixel grids where you have red, green, blue matrices, and each entry in the matrix represents a pixel color value, say 8-bit color. You have 0 to 255 for each of these values. So just incredible data. And then I was really happy to add this one of an example of text data. In March of 2023, the Owls made the NCAA tournament for only the 2nd time in program history, and remarkably made it to the Final Four in Houston. I was hoping maybe there'd be more written about this in Wikipedia, but this is an example of text where you just have a text sequence, and that's just a type of data. So as a super basic primitive of what deep neural networks are, it varies a bit, but basically you have this kind of structure of sequential processing where this kind of layer 0, the input layer, goes to layer 1, goes to layer 2, however many layers there are, and then finally some kind of output, generally sharing this kind of sequential structure and details about exactly how the computation is performed. But so kind of the first slide, and I've sort of intentionally made this slide kind of dense because I don't think it would be worth it going too into the details of this for this presentation. But the key thing is to understand the different computational primitives of deep neural networks and how they multiply their weight matrices with the previous layer's input to keep transforming the data. So the multi-layer perceptron describes this basic idea where you connect everything to everything in the next layer. There's a weight from X1 to A, from X1 to B, from X1 to C, X2 to A, so on, A to D to E to F. So it's just everything to everything, big matrix multiplication. Whereas most similar to the multi-layer perceptron would be the attention operation, where you transform the input with 3 separate matrix multiplications. You can when you have a matrix multiplication, if you multiply n by m times m by k, you end up with n by k. So you can, play with the dimensionality of this to make it computationally reasonable. So you have these kind of compression bottlenecks in the sizes of the matrices, and that's how you kind of, fit these onto GPUs and things like that. So there's also the convolutions, which is this weight sharing thing. But aside from the core building blocks, which are the computation layers, whether it's the parametric layers or say it's like a normalization layer to scale the activations, you connect them in these architectures. So the transformer architecture, generally neural architectures consist of microcells and macrocells. So a microcell would be something like you take the input, pass it to an attention layer. You also have a skip connection that takes that input to the output of the attention layer without a computation, then has some other thing, maybe normalization in the middle. But you take these cells and you build up the sequential structure with them. And there's a pretty interesting area of research for finding the optimal configuration of neural networks. What's the optimal configuration of convolutions, attention, even say normalization layers, activation functions, and searching through this usually with a black box optimization technique. And this is an important detail because we're going to come back to this with the data augmentation controllers, is you manually define a search space and then you have some kind of technique to parse it. And so just a quick overview of neural architectures. The next important topic, as we're covering the introductory topics in deep learning, is about labeling data for learning. And the next slide will give you a quick overview of the math of gradient descent. But basically, you need some kind of loss function to try to make this output equal to. When you have this y prime, you're trying to get it to some kind of y. You need some source of the y to compare this y prime with. So in supervised learning, this has been most of the foundation of deep learning. This is where humans label each data point, each say x1, x2, each image, each text sequence, and say it should have this y label. And so that's where you get the source of supervision. One of the most exciting recent breakthroughs of deep learning has been self-supervised learning. Self-supervised learning means that we no longer need to manually annotate the data. We can algorithmically extract the label from just say like scraping the internet. And that's this language model thing, is you take all this internet text and you randomly mask out a word and then you predict the masked out word. So you don't need a human to be labeling the masked out word, and then you can scale this really enormously. Reinforcement learning is another super interesting category of learning task where the key difference between reinforcement learning is actually very similar to kind of sequence learning generally. Like if you study sequence to sequence, and kind of a lot of the text stuff has had this kind of like LSTM, RNN, this kind of like you make a sequence of decisions and then there could be consequences for earlier mistakes in later predictions. But generally the thing about reinforcement learning that I think separates it from the others is the reward signal is very sparse. You might make 10 predictions mapping from input to output before you see a reward signal. So you need to do that credit assignment. And that's kind of the really interesting thing about that category of learning techniques. So underneath supervised, self-supervised, and reinforcement learning, I put a few terms that are pretty significant. Multitask learning would mean you're trying to optimize two labeled tasks with the same input simultaneously. Transfer learning would mean you train on one task and then you initialize a neural network for the next task with those weights. Semi-supervised learning is very similar, where you have a mix of, you use some model that you're learning to infer labels and then you kind of self-teach it this way. So it's an interesting kind of class of techniques that I don't think has been so popular lately, but when I first started, this was a pretty interesting when the emergence of self-supervised learning. Weakly supervised learning then describes similar to self-supervised learning, where you use heuristics to label the data. And then meta learning is where you have this outer inner loop optimization. So to step into the math of gradient descent, the key is that you have some y that you're trying to align this y prime with. So say the weights of d would be updated to d equals the loss plus this learning rate times the differentiation of the final output, the loss with respect to d. And then a, you send the gradients back by differentiating from L to D, and then say also the D, DD, DA, DE, DA, DF, DA, differentiating across this to see what A contributed to the final output and then update it accordingly to where you're trying to steer the neural network to. And then finally, this super exciting topic that I'm going to dive into more later is this concept of how generalization is measured in deep learning. So generally what you have is you have a pool of data and you randomly sample the training set and randomly sample the testing set from the same distribution of data. And that's kind of the fundamental assumption of statistical learning theory. And that's key to how these systems are measured. But then when you're applying these systems in the real world, it becomes such an interesting topic. So that concludes an introduction to deep learning. Now we'll get more into the topics that lead us into data augmentation. So we're starting off with overfitting. So to begin, overfitting is sort of something you can see quickly when, as you're training the model and the training loss starts to increase, the testing error increases as the training loss continues to decrease. So it just gets really good at predicting the training set, but that doesn't generalize to the held out test set. So the desired convergence would be that both of the losses go down together. And a bit of an explanation of why this is, in statistics, you see things like, regularizing the variance of functions. So say you have this, this line has too low variance to fit these points. So if you see the solid blue line, that simulates the function that's being learned. And the orange is, say, the true distribution of the data, and then the blue dots are the data points. So degree 1 means it just, the model doesn't have the capacity, it can't model the data at all. Degree 15 means the model has so much capacity that it just learns a silly line to map all the points perfectly, but then you find some optimal capacity of the models. But we'll come back to this, but in deep learning, you would think the intuition would be that you're talking about degree 15 cases all the time, but it's such an interesting kind of thing between this super high dimensional parametric models and then super high dimensional data and losses and all that. So this is a good way to think about it a bit, but this doesn't quite explain how it is in deep learning. So a little bit more about what this looks like in deep learning. You have things like this image of mountains, this kind of static image or a medical X-ray or a question answering task. And once you put this into high dimensional input data, there are all these super fine grained patterns in the input that the deep neural network with its super high capacity processing super high dimensional data will learn these particular things that correlate with the labels. And so it won't really learn, say, causal factors of the input data that cause the label, but instead it learns these correlations between these super particular patterns in the input data. So the original interest in data augmentation, and Dr. Koshgofter introduced me to this topic as a way to solve this problem of overfitting. So the way you solve this problem of overfitting is, say you're doing this skin cancer classification task, and you, instead of say you only have 10 examples of this. If you model the 10 examples with a super high capacity model, it just decreases the loss in the training set with no generalization to the test set. But by augmenting the image, by transforming it in a way that preserves the semantic label, you can blur out these super high frequency subtle patterns in this really massive input matrix with all these fine-grained patterns between the 0 to 255 bits in each of the pixels. So by modifying it with these label preserving transformations, you simulate a big data set, and a big data set can help you regularize this high capacity deep neural network model. So before continuing more on data augmentation, it's worth saying that there are other regularization strategies for overfitting. So dropout is a strategy where you randomly zero out intermediate activations in neural networks, and that way you cause kind of the whole model to be robust in that sense. It also kind of helps it with sparsity. So that kind of regularize the architecture itself. Batch normalization is where, similar to how you normalize tabular features for input to deep neural network or any machine learning model, you say take each value and subtract it by the mean divided by the variance, minus x max over x max minus x min, these kind of things. You put that in the intermediate layers of the neural network to scale the gradients and, avoid things like NAND loss if you've trained neural networks and that kind of thing. So then, neural architecture design, it's kind of related to that idea of trying to find the optimal size of the neural network for the data you have ensemble learning, where you say distribute the predictions across a cluster of models trained on different subsets of data or with different architectures, different training strategies. Pretty interesting idea, ensemble learning. And then transfer learning. Transfer learning has been the most successful thing in deep learning. So you pre-train a model by doing that language modeling, self-supervised learning task, and then you start with those weights to learn some supervised learning task. Let's say you only have 50 labels for, which is the core problem with this overfitting, where you're trying to learn from limited label data sets. So now let's dive more into data augmentation and what data augmentation is. So starting off with image augmentation, I think I've already kind of hinted at this idea of a label preserving transformation. So say you have each of these 4 images and you apply a rotation to them. So this rotated boat, you still would classify this as a boat. The Y would still be, boat, similar with, the airplane and the frog. So that's generally the idea, is trying to identify all of the ways you can transform an image such that you kind of blur out these high frequency patterns. And hopefully by doing that, you get the model closer to learning causal factors, like this is a dog because it has this kind of nose and these kind of ears, to discriminate that it's a dog compared to a cat, compared to just these 0.12, 0.13 patterns in the matrices. So the first task in my dissertation research was to just survey the literature and see every kind of label preserving transformation that's been discovered. So you start off with basic image manipulations. With what you're looking at is a geometric transformation of a rotation, where you can multiply the input image by a rotation matrix, and that's how you turn the matrix, turn the image. Random erasing would be, you say crop out a patch of the image. Increase, say, the red, green, blue, mixing images, where you say average the pixels of images together. Kernel filters, like a Gaussian blur, where you take like a 3x3 kernel with, say, like 2, 2, 2, 2, 0, things like this. And, the patterns in the kernel that you can use to sharpen the image or blur the image. And then there are deep learning approaches like where you use a neural network to infer the transformations in the data to then feed to the student model. And we're going to come back to that at the end, because that is a crazy exciting topic. So then coming into text augmentation. So I started doing this research in images and computer vision, and then I saw this thing that was happening in natural language processing. Obviously, it's super obvious with ChatGPT now, but at the time it was kind of like a decision, like, do I want to keep doing the computer vision stuff, or am I going to start to dive into the text and the natural language processing? So I decided to do the text thing. And so to start off with, easy data augmentation is a good introduction to this, like the analog of the kind of rotation, like something that, preserves the label pretty reliably. So random swap, you say replace I am jogging with I tiger jogging. Random insertion, I am jogging, I am salad jogging. These kind of things where you transform the text. And so the key thing to note about text augmentation that's different from image augmentation is that it's much harder to preserve the label with the transformation. Random deletion, if you I don't know, if you're classifying intent in a search engine or something, and you're trying to see like what this person is doing, and exercising is the label, and you delete jogging, so it becomes I am jogging to just I am, you've completely lost the information for the example. And so it's harder to keep it label preserving with the text transformations. Okay, so those are kind of 2 categories of how this is applied. And so kind of finishing the theoretical section with this concept of generative augmentation. So typically what we would do is we would be kind of hunting for these heuristics of like rotation or horizontal flip or Gaussian blurring that preserves the label. But now what we can do is we can train generative models that can learn the underlying data distribution and then produce novel examples to train with. So I began studying this with the generative adversarial network architecture, if you see my mouse on the left. So the generative adversarial network framework for generative learning is where you have the real data set, say this is the 1,000 examples of cats and dogs that you have, and you'll sample a mini batch of real examples. So say this is 16 dogs and 16 cats. The generator network is a neural network that will transform a random input vector into images. So then you mix this mini batch, real samples, say these are labeled as 1, these are labeled as 0. This goes as these are concatenated and put as input into another neural network, which is the discriminator network. So this network is trained to classify whether the image came from the real set or from this model. And so then you send that loss back to update the generator, as well as to update the discriminator. This is a pretty interesting idea that worked pretty well. It generated photorealistic images of up to 1024 resolution, so it was pretty successful. But it also was quite difficult to manage the learning dynamics of two neural networks at the same time that are optimized in this kind of adversarial way. Nowadays, you'll see more cases of like two neural networks being optimized, but it's usually in a teacher-student sense. It's pretty uncommon to see this kind of adversarial optimization with deep learning, just as the time as I'm recording this talk. Then what came along in image augmentation or generation is diffusion models. So diffusion models is where you, at each time step, you add some noise to the image until it's imperceptible, and then you reverse the process. So by, in this example with this dog image, say you have these seven, the six next to each other, you can see how you can use these neighboring pairs as the training data to map from this to this. And that lets you bootstrap a ton of data to regularize the neural networks with, and it just has shown to work pretty well. So then on the other end, back to the text side of things, there are the language models, and the language models have gotten really good at this. So what the language models do is they predict a masked out token and go on. So, now it's gotten to the point where you can say, please write a negative movie review about a fictional superhero movie, and see how it does this. Superhero fatigue is a term that's been, so imagine you're training a text classifier on, IMDb, like movie review sentiment. And now you can just generate this training data like this, because you could prompt it to say, please write 1 million negative movie reviews. And now you can regularize a deep neural network because you have 1 million training examples to learn from. But the interesting thing is kind of the controllers for augmentation. So we have these different ways of sampling these augmentations. So even in the case of rotation, you have a hyperparameter on how much you want to rotate it. Do you want to rotate it like 5 degrees, or do you want to, really flip it 90 degrees? So you have this inner outer loop optimization where usually what you do is you just have like a 10 by like you define a grid of hyperparameters, and you'll just kind of randomly search through it, or maybe you'll have like a Bayesian optimization or an evolutionary algorithm, but like a no gradient kind of optimization on top of that. But one of the cutting edge categories is actually putting gradients from the outer loop into the inner loop. So what you're looking at on the screen is a paper called Generative Teaching Networks. And what you're doing is you're trying to generate a training data set to optimize for MNIST classification, which is like handwritten digits. You take an image of a digit and is it 0, 1, 2, 3, 4, 5. So what it does is it's trying to optimize a set of 50 images that you can then train a student model with, and then it can classify this held out test set of real data. And one of the things that is so exciting about this is it suggests that maybe you don't need any real data to learn from, only to test with. And that's probably, I think, how this will change everything in the space of generative augmentation, is that the data, whatever data you have, is more of a testing thing than it is for the the data itself that goes into the gradient descent. So now we'll cover generalization. So generalization is the key of how do we measure the intelligence, broadly, how do we measure intelligence? So as we began, the fundamental assumption of statistical learning theory is IID data sampling. IID stands for identical and independently distributed data. So to kind of break that down a little bit, identical means that they're all sampled from this purple distribution. So, you have 1,000 examples of cats and dogs, and they all come from the same distribution, however that is. And then you sample, say, the 800 for training, 200 for testing randomly. So that's where the independently part comes from. There's not like a causal factor that causes this testing set to be, not independently sampled compared to the training set. But in the real world, we have this thing called distribution shift. So distribution shift broadly describes when the testing set is sampled from a different distribution than the training set. So that inspired my interest a lot into thinking about, what does that mean to have the distribution be different? So I think generally it's very interesting with this whole time series concept of it, where, most of the things you say train from, 2012 to 2020, and then you go on to 2021, 2022. And there's a great example of, when they talk about COVID-19, and the models they have no understanding of COVID-19 because they've only been trained from 2012 to 2020. But researching this a bit, I found 3 other very interesting cases of distribution shift and some general categorizations of it. So to start off with robustness describes generally, having this model make sensible predictions, and kind of like the simplest term, this robustness thing. So, and this is manifested in 2 ways. So to skip ahead a bit, I'm sure you've all seen this picture where you add this noise map and then it can't classify the panda anymore. And so that's kind of the idea of robustness, is like these inputs that are like, it doesn't make sense that it fails with these inputs. So the first category of robustness that I think is way more interesting is natural robustness. So, back to the augmentation, and the reason this connects to data augmentation is when you rotate the airplanes, and this is the paper that won the best paper award, is showing this, is when you rotate the airplanes, it can't classify the airplanes anymore. So it's like, how useful is a model that can't classify you add noise to it and now it can't classify it at all. So it just shows that understanding the testing of it is so badly understood. But so natural robustness is where you construct test sets where it's the same exact test set, but transformed with this set of 15 augmentations. And so in this table, what you're looking at is the error rate. So with the ResNet 50, the best performing model shown at the bottom, if you can see my mouse, it has a 23.9% error rate. Now, when you augment that same exact test set with Gaussian noise or blurring, or say adding this kind of snowy weather effect, the error rate increases to, say, 100% for the AlexNet. It can't classify it can't classify anything, and all these things. It's just insane. And we'll get more into the details of this with the experiments that I've conducted. So this is also the case with natural language processing models, where you say, insert negations to "I can't say I recommend the food," or "I didn't." You insert "didn't," and then it can't classify the sentiment of some text anymore. You say replace, Chicago to Dallas for a named entity recognition task, and it still thinks it's Dallas. Or you swipe out the vocabulary from like "you are lame," things like this. This is where you insert some text that should make the movie review more negative. So say you have a text classifier and you insert like some horrible sentence at the end of the movie review to see if that results in a more negative prediction. And a lot of the time it doesn't. So then adversarial robustness is maybe more of the well-known thing because of how ridiculous this image looks. But what this is doing is you're putting gradients directly into the input to cause the misclassification with optimization. So to me, this isn't realistic. I don't think this is the kind of failure case that we should be worried about with deep learning, because access to the gradients to optimize the map, like you're not going to be having a self-driving car in it, or a medical image. Well, like obviously the networking and how all these systems are implemented is obviously important with security and all that kind of stuff. But just in terms of the phenomenon of intelligence and how it's useful, kind of seeing a stop sign, is it going to have an adversarially optimized noise map on it? Probably not. It's probably more the case that it's snowy or it's dark outside. And this is also the case in natural language processing. You can optimize to have, particular words that you flip or sentences that you inject to cause a misclassification for all the, question answering, all the NLP tests as well. So the next category is really an excellent categorization of generalization testing. This is a paper that came out from a big group of labs called WILDS. And if I was recommending a data set for someone to start their PhD research, I would say WILDS is the data set to check out. And shown in this bottom left, this is the citation for how to find it. And it's cited in the dissertation. Domain generalization describes transferring between domains. And I'm actually going to show you this in images really quick, because images is a great example of this. So say you classify sketches of pictures, like airplane, clock, axe, and then you have the photorealistic images, the quick draw, a painting, an infographic, or clip art. And so similar cases, the robustness, you train on this, can't perform at all on this. And so that's the concept of transferring between domains. And we're going to get into a really interesting experimental study on, looking at what this looks like with different information sources for NLP processing, but we'll get to that later. And then the other key topic is subpopulation shift. And so Dr. Koshgafter has taught me a ton about class imbalance. Class imbalance is where you have a minority label distribution. So say 95% of your images are one class, 5% the other. It's going to be so biased at predicting 95% class. And when we cover the COVID-19 experiments, this will be, I'll explain this in more detail then. So now we'll start talking about the image classification experiments. And so this also concludes the kind of theoretical portion of going through, what is deep learning, what is overfitting, what is data augmentation, what is generalization testing. And now we'll get into the results of the kind of concrete experiments that were conducted during this dissertation. So we'll start off with the image classification experiments. So we have airplane, car, bird, cat, deer, dog, frog, horse, ship, truck. We have these 10 different categories for classification that we're trying to have a model predict the category for this classification. So it takes this image as input and it predicts that this is an airplane, this is a bird, that this is a cat, and so on. So what you'll probably first notice about these images is that they're very low resolution. And this facilitates the computational burden of conducting these kind of experiments. These are 32 height by 32 width images. So what that means more concretely is that you have the 32 by 32 with 3 matrices of these together, and then you have the mini batch of say 32. So it's really about doing the math of 32 times 3 times 32 times 32 times 255, and then that's the size of the tensors that are going in as input, and then you have the same size tensor that comes back with the loss function. So it's about, can you fit that tensor within the memory of the GPU that you have access to? So when I first started my dissertation, I had a 4 gigabyte GPU that I set up myself. And so you had to use data sets like this, because there was no like putting ImageNet onto that 4 gigabyte GPU unless you applied all these. Nowadays there are things like gradient checkpointing, but back in the day that would have been just a crazy task to have done the engineering of making those gradients not have out of memory allocation errors with a lot of, and obviously memory allocation is a huge topic in computer science more broadly. So starting off with the experimental research, and this is the paper that won the best paper award, is I was just captured by this phenomenon. I had to kind of see this for myself. So, and then kind of coming up with a research question, because I wasn't just gonna, because I had done this review process one time and got to know kind of the way that this is played a little bit. So looking at like, what is another research question that I can kind of add into this discussion? So I chose the architecture ablation. So the architecture ablation is saying, is this robustness problem different for the convolutional based ResNets compared to the attention based vision transformers? And the other thing that makes this interesting is because convolution, there's this huge topic in deep learning about inductive biases, how however you bake into the learning process to be biased towards one particular kind of solution class. So attention networks, they attend over the entire image at once. So they have this global inductive bias to look at everything in the image all at once. And similarly with text sequences. Similarly, a lot of these data augmentations preserve the entire structure of the image. So, when you horizontally flip an image, you preserve the kind of global context of it. Whereas if you crop it, you are now focusing on a local inductive prior. So the convolutional kernel is also a local bias, where you have this local kernel that you're using to say, focus on these little patches and kind of, aggregate that to form your prediction. So you have these 2 different kinds of inductive biases that bias the learning process to have, particular kind of solution class. So the research question was, is that true? How did the inductive biases because again, this is super high dimensional data, super high dimensional parameters in these models. So is that intuition about inductive bias, can we kind of experimentally reproduce that by isolating the ResNet architecture compared to vision transformers, and then isolating the global priors of different augmentations versus local priors of different augmentations? And unfortunately, we weren't able to find that connection, but we were able to kind of experimentally understand a lot more about this problem generally. So let's start off by saying, what happens to these models when trained with augmentation versus without augmentation? So what you see is a ResNet, when it's trained without any data augmentation, achieves that thing we saw where, it's decreasing on the training set, but it's overfitted to the training set, further decreases in the training loss, spikes the test loss. So, not good. And this is the whole motivation for data augmentation. If you can see the difference between the trained tests, it's just kind of obvious why you use this. So the first interesting thing that we found is that these vision transformer models, they take longer to train than ResNet. So we had to go across, say, 500 epochs with the vision transformers. So then to come a little more into exactly what augmentation strategy and what that looked like, you use the rand augment sampling where you take 3 different augmentations to apply in sequence, and then they have an associated hyperparameter with how strong the augmentations are. But just to get a quick look at this. So again, the vision transformers, they took longer to train. So if you consult the dissertation, if you consult the research paper, you'll see all these details behind how we tried to put the ResNet and the vision transformer on the same scale, because the ResNets, you only need to train it for 100 epochs, whereas the vision transformer, you need to train it for 500 epochs. So it's hard to just, in a very scientific sense, just completely control all the potentially confounding factors and create this causal tag of what caused what, with this idea of isolating architecture biases with augmentation biases. So the first test was the crop testing. Crop testing is where we have the local prior. And so we did find the ResNet to perform a bit better than the vision transformer, which was kind of exciting. But as the cropping gets more extreme, they both kind of perform similarly. And so this is a plot of comparing the vision transformers trained without augmentation with augmentation. And then the next test was the noise testing. So this is where we applied Gaussian noise onto the images to transform them. And so, this is what happened where we took the originals and we applied these different noise ranges. And bizarrely, we got the same test set for the same loss for all these different magnitudes of augmentation. So we plotted it just to show you that we've done this correctly when we're doing the experiments. And so these images and these images, they perform exactly the same on each other. So it's kind of just a funny thing to have seen. Then the next set of experiments was diving into potential solutions for robustness. So how can we maybe improve the robustness of deep learning models? So one idea was to have a consistency loss between images before and after they are augmented. So you have this ship and it produces this representation vector. Then you have this transformed ship and you say, do these perform the same? You apply the loss function not only on did this also predict ship, but also did it predict the exact same representation as the original image when transformed in this way? And so we found really great results with this. This paper is done okay. I thought this would be more popular, honestly, but this kind of idea of applying this consistency works really well. And it's not necessarily the accuracy you should look at, but it's what we introduced a new distance measure called distributional distance, where you take the entire original data set, compress it into vectors, and then you compare the vector distance between each of those with the same data set transformed with the augmentation and compressed to vectors. So it's the vector distance between, in the dense layers of a particular convolutional architecture, compresses the tensors into vectors. And so you compare these vector distances. And then what that means is that it's invariant to the transformation that you've applied and thus is more robust. And then we also did show that with increased performance on the rand augment test set from 80.6 to 83.3, but I think there's so much more that people can do with this kind of idea. So the next class of experiments is, I think, something that is really profound for the kind of future of software engineering. So I was really inspired by, Dr. Koshgavter had done some research in software quality control with machine learning, where you have these just gigantic code bases. And so you try to extract features to detect bugs that maybe a compiler would miss, because like the memory issue bugs, things like that. It's not so easy for the compiler to always get it. So you might try these parametric models to do it. And then I was just so inspired by the, at first they had this GitHub Copilot model that was a language model trained on all of the code from GitHub. And it was pretty remarkable. So the start of this was, I was using this programming framework called Keras to run these experiments. I was really interested in this. So I was curious, how well can a language model trained on all of the documentation, like everything we can find about Keras, how well can this write Keras code and answer questions about Keras, solve the debugging, and just in the sense, truly have like an AI that improves itself by writing its own code for the things that you do to train these models. So that's kind of the grandiose sense, but stepping into the concrete details. So what you're doing is you mask out one of the tokens, and then class groups layers into an object with training and inference features. So the ground truth is model. So you took this snippet from the Keras information page, masked out this token, and it's predicting these masked out tokens. So another example, a callback is an object that can perform various actions, stages of pre-training. So this is just so this is like the information about Keras. Does the model, can it fill in the masked token? Can it predict these things? So quickly, before even diving into it, here's like a picture of what the text looks like. So this is the domain generalization thing. So we're coming back to that domain generalization in images. It was this concept of you have the drawings of an airplane compared to a picture of an airplane compared to clip art. Within text, you have these different styles of how information is written. So this is an API reference. An API reference, software is typically organized with like inheritance and this kind of thing, where you have these objects with the abstract functions, and then they inherit, modify the functions in these kind of ways. So it has this particular kind of documentation structure in software where you have, the model class, and then, you list it out by defining its input arguments and like what you would expect it to return, a snippet of how to use it generally and how it connects to other. So it has this particular kind of structure. The Keras code examples are written as like tutorials. So it's like, here's the introduction, here's the setup, process the data, load the training loop, optimize, test it. So they have these two different styles of writing. So on the left is the initial data set we collected. 67% of it were code examples like this, and then 23% of it was API reference like this. Then as we followed along with the book chapter, we grew this data set. So now we have Stack Overflow question answering pairs, Medium articles, which are more casually written even than these. Then we have GitHub repositories that use Keras. We have Kaggle notebooks. Kaggle is like a competitive data science platform. So we took all the notebooks that use Keras, and then this percentage of data set now occupies this much of the data as we've updated it. And even the Keras code examples, a lot of new ones came in as we were updating it. So this, I think, is such an important thing to know about how these data sets will evolve, the kind of composition. So we talk a lot about class imbalance in the sense of just the label, but it's also in the sense of like the sources of the data. And so that's exactly what we sought to measure. So we started off with kind of initially trying to model these, and we found this kind of overfitting where we would, it would initially drop off and then it kind of plateau. So these are kind of what the loss curves look like. But really what we wanted to study is how well does training on the Keras code examples generalize to the Keras Kaggle notebooks? Or, if you read the API reference and, you read the API reference so well that you can predict every masked out token, does that mean that you can now predict the masked out tokens for the code examples and things like this? So what you're looking at in this graph is, I'd say focus on this column, which is the average test loss, where you train on one source and then test on all the others. So what we found was the Keras code examples was, say, the most informative data source, because we have this 4.25 test loss, whereas the API reference actually gave you 6.33. So reading the API reference didn't generalize. And why is this? Is it because of causal factors where it's like the API reference is misleading? Probably not. It's probably because of the style and the high frequency patterns that it's learned to overfit with the style of the reference guide. And whereas those high frequency correlations, as you turn text into big embedding matrices and then process it with transformers, the code examples have probably the most similar, like if you think about an interpolated space in the massively high dimensional space, it has the most generalizable style to it. Hopefully that's like concrete enough. So kind of concluding the paper, we wanted to compare it to the zero-shot language models. And this is such an interesting category because the zero-shot models, they haven't been trained on the data set, on the source you're testing it on. So this is the model we tested on, the pile. So it's been trained on PubMed, Archive, all these things, GitHub. And so we tested how well it can, it can finish answering these things. So the key difference also is these are GPT models, which means that they decode at the end of the sequence, whereas BERT predicts it in the middle of the sequence. So we gave it this prompt and had it run out some generations. And since we published this, we've seen the release of ChatGPT. So if you see this generation, you ask it, to answer this question, the summary method of the model class raises a value error if summary is called before the model is, and then you see it explains the summary method. It gives you a code snippet. This is all generated from a language model. So it's just absolutely mind-blowing. So the next set of experiments was a pretty serious thing, which was the COVID-19 patient survival classification experiment. So firstly, this was an interdisciplinary effort with a team of about 12, Dr. Koshkofter and myself representing the Computer Science Engineering College and then FAU College of Nursing and collaborators from the Memorial Healthcare System that provided us with the data. So we had, the first task really was like the ETL of looking at this data set and communicating with the stakeholders on their side and being like, okay, what are all these features? So that was actually a pretty big task that maybe if you're used to these kind of academic data sets for machine learning, that it's like already perfectly curated for you, you don't think a lot about this problem of like the data might not already look like the UCI machine learning repository. So we first parsed out okay, what features are we going to use? So we decided to start off with a mix of demographics and previous conditions. So we started by predicting the initial treatment decision. We did some experiments with class imbalance where we were looking at ablating this sampling parameter of random oversampling. So as mentioned earlier, when you have a majority class and a minority class, it's going to be so biased to predicting the majority class. So what you do is, and when each batch of data goes to the model, you oversample from the minority class. So you will duplicate instances such that you have, say, 12 to 4 in the mini batch compared to, say, 16 to 0, where obviously 16 to 0, the gradients just only push it in that direction. So there's no, representation of the minority class. So then what we did is a set of experiments that I think are really interesting. We looked at if we could apply transfer learning from text into this data set. So transfer learning has been super successful, where you do language modeling on something like all of Wikipedia, and then you transfer it to, say, tweet or like election polarity is a set of experiments that came from predecessors to me in Dr. Koshkofter's lab, that I saw this phenomenon of they were pre-training the model on BERT, and then they would test on, say, Yelp reviews or the election polarity thing. So this kind of idea. So how would we do this for these tabular structured data? So the key to that, before diving into the data set a little more, is to prompt it, where you prompt how you translate a tabular feature into the text, and we'll get into the details of that. But let's dive a little more into these experiments where we're predicting survival or patient outcome. So the first thing to note maybe is to, just something we put in the paper was a distribution of age with respect to mortality, because that's a pretty predictive feature. And just to give you a sense of like what the task looks like. So then to come a little more into class imbalance. So most of the patients did survive in our data set. So it's about 85% to 15%, which means that if you report accuracy, your 85% is going to look pretty good, but it's only predicting the positive. It's absolutely useless for the task that you're doing. So you have to look at these metrics where you compare the true positives and false negatives, false positives, true negatives, and you have metrics like precision, recall, F-score that give you an actual sense of how the model is performing. So when you see the final chart, you'll see that the random forest model has the best accuracy, but that doesn't mean anything. So kind of flying through the details of this, and again, the concrete experimental details can be found in the dissertation, but we tested random forest, logistic regression, deep learning models that process tabular inputs. Then we ablated the different ways of translating tabular data into text to transfer learn from the transformers. And in the end, what we found is that the lift transformers, where we transfer from Wikipedia, perform about the same as a deep learning model optimized on tabular inputs, as well as the oversampling. All the details, again, are in the paper. And they both perform better than the random forest. But I think there are so many things that make this interesting, because there's so much more exploration that can be done into the space of the transfer learning. Because Wikipedia is like, is that the best pre-training domain? Maybe if you pre-train on PubMed, maybe say, applying ChatGPT as in a retrieval augmented sense to this would perform well, but there are so many questions to all that kind of stuff. So to conclude with kind of a couple things, just a quick overview. We also produced this paper, Applications of Deep Learning for COVID-19, myself, Dr. Koshkofter, and Dr. Furt. So we reviewed all these different applications. So if you're curious about what deep learning looks like for all these particular applications, it has a coverage of all these things, citations of things like AlphaFold or vision-based robotic systems that can maybe do different tasks. And we're really happy to have had this paper endorsed by the MIT Computer Science Lab on Twitter. And also, as of now, this is the most cited paper of this category of like AI for COVID, data science for COVID. So here are some conclusions and future work and things maybe I'd recommend to PhD students listening to this talk. So firstly, when I did the COVID paper, I was saying, what are the current limitations of deep learning? Learning from limited labeled data, like training a classifier on 50 examples, that's what started my PhD research in data augmentation. That I was obsessed with that problem. I was trying to classify made baskets in basketball games, and I saw this problem where if you're trying to collect like a million scale data set of something, it's just super limiting to applying these kind of algorithms. Then as it presented with generalization metrics like robustness and domain generalization, subpopulation shift, we don't really understand how they fail that well. And then there's things like interpretability and data privacy. Interpretability is, roughly describing the kind of trying to identify causal factors. It's very similar to like the motivation of data augmentation, where you want the predictions to be based on causal things like the dog looks like this, not because of some crazy pattern, like static pattern in the image matrix. So, and then data privacy is, especially as we did the COVID-19 experiments and understanding what all that entails, you can't just like collect medical data, insurance data. So a lot of these things, there's gonna need to be more like innovation in things like federated learning, differentiable privacy. It's not just gonna be like an open source million scale data set for those kind of things. So here are my recommendations for future work. So the first thing is with ChatGPT, it's been able to perform these tasks without training data, but then it's so large and it's so expensive to run. So the distillation of the large generative models to smaller models, and I think generative augmentation is the way to do that. You generate data for a particular task with the large model, and then you use that as the training data for the smaller model that's way more cost effective to learn. And then there is sparse transfer learning. So even this smaller model, it still might be transfer learned from some checkpoint. It's not like a randomly initialized model. And so maybe the generative model is like a trillion parameter model that costs like $1 billion to train and lives in a big lab and stuff like this. That generates the data. And then I imagine that'll be like a 1 billion parameter model that you transfer learn from. And so transfer learning, not quite at the large scale, but there's this sparse transfer learning thing where you don't need to update all the parameters. There's a way to sparsely update to the new task. So then there's a problem of longer inputs to deep learning models. Is we talk about maybe deep learning models that can process videos or say entire code repositories as input at once. There's a lot of computational problems behind, say, designing the attention layers and things like this, things like flash attention. How do you fit those gigantic inputs into deep learning models? Then there are two phenomenons of deep learning that I think are really interesting. The first of which is catastrophic forgetting and continual learning. Say we want a model to just keep on learning the same model, but there's this thing where if it learns task A and then task B and then task C sequentially, by the time it's learned task C, it will have forgotten task A, and it's just like a collective, like, well, who knows why. Then there's scaling down deep learning. So this was a position paper that I really agreed with it, and I thought it was interesting because it's saying like, when you experiment on CFAR10, MNIST, or IMDb, do the lessons. So say we come all the way back to that idea of the inductive biases and how that correlates to the architecture biases. Does that actually tell us anything about these just gigantic models like ChatGPT and so on? So everyone, thank you so much for listening to this presentation. I hope you thought it was interesting. I'd be more than happy to answer any questions. And of course, thanks again to everyone at Florida Atlantic University who has helped with my education process in studying all this.
Thank you, Connor, that for an excellent presentation that, by the way, originally had 30% more slides. I cut that to make it to the 1 hour. So this is very important. As some of you may know that I have supervised many PhD students, close to 40 or so on. This is one of the best that I have seen that in my whole life. Not only my group, entire university. So I can say that Connor is very, very successful person. He understands, he knows what he's doing, and so on. And I was very, very fortunate to have him in my research team. By the way, he started from undergraduate study with me through the graduate study. So it's quite what unique that. First, we would like to ask the committee member if they have any questions. Committee member?
So no question for me. I just congratulate you, Connor, for such a great research and presentation. Excellent work. Keep up the good work.
Okay, I have a few comments or questions. First of all, Connor, you did a phenomenal job. You were my student in 2 classes, as you mentioned, and you published papers, 9 papers. Everything is fantastic. My first question is about theoretical part that you presented. You mentioned a number of learning algorithms, and then you concluded that transfer learning is like the winner. Why do we have the other learning algorithms if transfer learning is the winner? Why do we talk about assembly learning or any other learning? Are there any applications where transfer learning is not the winner?
Yeah, that's an incredible question. I think there is a bit of there's still a bit of nuance to it, and I'd say you kind of would. That's kind of why. Sorry, I'm gonna take us all the way back to that. But I've kind of tried to categorize it in like the top and the bottom, where the top is like how you get the label, and then the bottom is like the mixing strategies between the optimization tasks. So transfer learning, usually what you're talking about is first pre-training the model with self-supervised learning, and then fine-tuning it with either supervised learning, or starting like very recently with ChatGPT has been reinforcement learning from human feedback, where reinforcement learning has mostly been like game playing AI and like robotic continuous control, and now it's finally starting to kind of be that latter end of the transfer learning. But I think it's about also when talking about the ensemble learning thing, it's like I think in addition to just how well can you make this model perform, there's also the how much is it going to cost me to serve the inference of it. And so that's kind of, I think there's still a lot of nuance to the research question. So I'm sorry if I annotated this like transfer learning is just the winner of all the things. It's probably the most exciting, but there's also the question of the cost of transferring from those gigantic models.
Okay. My second question or comment is, you did all these new things and algorithms, and is it anything, did you ever think, you and your advisor, Dr. Koshgofter, to have a patent on something? Because this is now the trend, and Dr. Merjad knows he has several patents, and we have in our group the patents. Now, when you come up with something innovative, then you can patent, which can be useful not only for your resume but also for FAU, for receiving maybe royalties for the patents. And I'm sure that in all your work there is some space for patenting, the algorithms, new algorithms. What do you think about this? Probably you didn't think too much about patenting.
Yeah, I did. I haven't thought too much about it, but I would, if you'd be interested in like you and I talking more about it, it would be interesting to learn about it. But yeah, I haven't, I haven't like.
No, I understand. Yeah, usually we have to develop this culture because we are developing so many things, and companies are then using and taking advantage of our work. Instead, we patent, and then you can always get royalties. We FAU and us. And we have a project in video coding, just to mention, where we have more than 100 patents, and FAU is already getting money, and investors, including some students, are getting money, So this is completely different direction, not only publishing, which is phenomenal and important thing, but also patenting our work. And big universities like MIT, they have, and Stanford, they have thousands of patents.
Yeah, I agree with Borko that during my career, I really didn't pay too much attention to patents and so on. But I can say that based on my search, some other people wrote many patents that and then they cited my work. So I didn't, I think this is really what the things that I didn't pay attention in my whole
Yeah, this is what we didn't develop this culture. And
yeah.
Tagi, instead of having 800 publications, if you have maybe 100 patents, you would be a multimillionaire today.
Yes, you are right. You are right.
Yeah.
Yeah. Yeah. I'm not saying that. Borko is my favorite person that they always think bigger the things. I look at so I don't go outside too much. But yeah, patent is one of the areas.
And now when we are in patenting world, it's unbelievable how relatively easy it is to patent. If you have a new idea, and there are many in this work of Connor's, then you can patent, and you never know who will come to knock on your door and say, can I buy your patent? Because they're producing something that they will use your patent.
Yeah.
So it's...
Yeah, I agree. Yeah.
Okay, thank you, Connor. Excellent work. I know you very well, and you deserve all this. From now on, next 2 weeks, we have to call you Dr. Connor.
Thank you so much.
Ding Ding and Hill, any questions?
Yeah, you have many good so many publications. Your research work is very impressive. I don't have questions. I just want you to share your experience of which part of your work is the most challenging, right, for you, and how you finally solve it. You can share this with I can see many other graduate students are there. You can share with others, right?
Well, I would say the three categories of experimental works have been challenging for different reasons, and then I would say the surveys have been, I've personally enjoyed that a lot. I really liked reading it all and aggregating it, and then the experiment. So I'd say experiments are a little more difficult than surveys, just in terms of what is more manually demanded, what's more demanding on you. So the image classification experiments with CIFAR-10. The hard thing about that is the reviewers, they'll say you only did this on CIFAR-10. So they want to see you do it across 10 data sets if you're trying to do image classification. And so that becomes quite a cognitive task actually to generalize your experiments to manage all these data sets as well as the novel thing you're trying to explore. So that's what makes that hard. The Keros bird experiments, what made that hard is I was curating the data set myself. So, it's more like writing web scrapers and parsing the output of web scrapers and stuff than it is about really about the exploring the experiments as much, because it becomes more of a data collection problem. Well, I'd say, and then also the COVID-19 experiments, that was also the data problem was the hard thing. This is the data privacy thing, because you can't. The frustrating thing was I really wanted to do the transfer learning with the zero-shot language models, where you translate it to text and then you put that as input as a prompt. And then we had Dr. Koshkofter and I were discussing this idea of a Bayesian prompt. So you have a prompt that tells it about the class imbalance. So, the prompt says this feature is distributed like this, the label is distributed like this. So you prompt it to tell it about the imbalance in the data set, and then you put in the example. Maybe you can mix the few shot. You could also kind of retrieve information in the prompt. That is the thing I wanted to explore, but you can't send data from the Memorial Healthcare System to OpenAI for the ChatGPT. So
Very successful, and congratulations.
Thank you so much.
Hill, any question, Hill? No questions, Hill? No
Hey,
questions.
Tagi.
Yes.
Yeah, sorry, I was juggling two meetings, but I think overall Connor did very good. I have no further questions.
Okay, thank you. Any other question by folks that attended the meeting? Any questions? Audience? No? And again, thank you for coming and joining us. That I appreciate it very much. About 19, 20 people attended. and thank you. I think this is the end of our about the meeting here or defense.